Okay, here we are on lesson 4 for week 1, synthesis of and bonding in phosphines, so generic PR3 and specifically PF3, carbenes, both Fischer and Schrock carbenes, also known as alkylidines, amides, and alkoxides. The bonding in phosphines is really sigma only, involving a lone pair on the phosphorus donating into the metal orbital. Some electron-withdrawing phosphines, such as phosphites, can have some pi acceptor ability, but that's best seen on the next slide for PF3, the most pi accepting phosphine. Electron-withdrawing phosphines also have sigma donation, so this type of interaction, but more electron-poor or electron-withdrawing substituents on the phosphorus actually reduce the amount of sigma donation that these phosphines exhibit. The pi back donation in PF3 and other electron-withdrawing phosphines is actually donation from a metal d orbital with electrons in it into an antibonding sigma star type of an orbital. So the orbital on the phosphine here is one of two degenerate E symmetry sigma star orbitals that you would generate using px and py as your generator functions. The synthesis of phosphines is really most easily carried out by heating or thermalizing the starting complex in the presence of phosphines and isolation of the product by precipitation. The sigma bond in a Fischer carbene involves donation of the lone pair on the carbon into an empty d orbital on the metal. Fischer carbenes are pi acceptors, and they accept electron density into an orbital like this one, which is bonding between the metal, the oxygen, and the carbon. So it has a very similar symmetry to that of an acetate type of interaction. So a delocalized bonding situation. Both the lone pairs on the oxygen and lone pairs on the metal are donating into the carbon. Because of a Fischer carbene's electronic structure, electron withdrawing, and with a heteroatom, it really behaves much more like an L ligand than an X2, so Fischer carbenes are L-type ligands. These types of carbenes are usually found on metal complexes in low oxidation states with other L-type ligands attached to them. So either a low oxidation state or a low valence number. The synthesis of a Fischer carbene usually starts from a metal carbonyl. A Grignard reagent or an alkyl lithium can do a nucleophilic attack on the slightly electropositive carbon, resulting in the formation of a new metal carbon bond. The metal carbon double bond is formed in this step, and then you can treat this complex with an electrophilic carbon. A classic example is trimethyloxonium tetrafluoroborate, which is one of my favorite compounds to say. It's a source of methyl plus, and so you can add the methyl plus onto the oxygen and generate your Fischer carbene. Schrock carbenes are also known as alkylidines to distinguish them from Fischer carbenes. Alkylidines, as the name implies, are really like alkyls. These ligands are X2 in character, not L. So one of the bonds comes from a carbon electron donating into a metal d orbital, and the other comes from the second carbon electron in a p-type orbital donating into a metal d orbital. The synthesis of alkylidines is not general in scope. It goes by a reaction known as an alpha abstraction. So this is an example of an X3M with two neopentyl ligands attached to it. One of the neopentyl ligands abstracts an alpha hydrogen to make neopentane, and then that electron goes to the metal and you form the metal carbon double bond. The bonding in an amide, the sigma bond is just what you would expect. A nitrogen electron overlaps with an empty orbital on the metal to form the first bond. Amides are strongly pi donating, and there's a second important interaction. The lone pair on the nitrogen can donate to an empty metal orbital, forming this pi type interaction between the nitrogen and the metal. Nitrogen amides tend to be planar. Because amides are strongly electron donating, they tend to be found on early metals, not later metals, which already have a lot of electron density. The bonding in alkoxides is very similar to that in amides, except now there are two possible pi interactions. And so metal alkoxides tend to be almost perfectly linear, but maybe not exactly linear. Like amides, alkoxides are fairly electron rich and tend to bind better to early transition metals. Although you can synthesize metal amides by a salt metathesis reaction, for example, taking titanium tetrachloride with 4 equivalents of lithium dimethylamide, forms the titanium tetrakis dimethylamide complex. However, these ligands can also be synthesized by a protonolysis reaction, for example, addition of isopropanol to a metal amide complex would replace one of the amides for the isopropoxide, liberating dimethylamine. Okay, it's time to check what you've learned. We have alkylidines, or Schrock carbenes, Fischer carbenes, which have a heteroatom, and then some organic-like ligands, alkoxides, amides, and phosphines. Classify these as sigma or pi, and X or L, and then go to the next slide to check your work. Alkylidines, or Schrock carbenes, are X2 ligands found on metals in high oxidation states with other X-type ligands. They are sigma and pi donors. Fischer carbenes are L-type ligands found on metals in low oxidation states with other L-type ligands. They are pi acceptors. Alkoxides are X-type ligands, but they can have 1 or 2 L-type donations depending on the exact complex you're looking at. They are both sigma and pi donors. Phosphines are sigma donors and in some cases pi acceptors for electron withdrawing phosphines. Amides usually are XL type ligands donating 3 electrons in a sigma and in a pi sense. There are other ways to classify ligands, including sterics and electronics. So the sterics is how big the ligand is. This can be measured in a variety of different ways, including the cone angle and the percent buried volume. Electronics is how electron donating or withdrawing the ligands are, and you can use carbon monoxide as a reporter ligand by IR, as we saw in lesson 3. I won't go into a lot of details on sterics, but this just gives you a sense. The Tolman cone angle was the original way to measure how big a ligand was, so it's a solid angle that is occupied by the ligand. Nowadays we can use other more computationally intensive methods to determine the solid angle or the percent buried volume. If you'd like to learn more about this, you can ask me in office hours. Electronics used to be measured by carbonyl stretching frequency, as we talked about before. Not all metal complexes can bind to carbonyls, and so one of my colleagues who works at Michigan State has used the rotation of a dimethylamide ligand in a chromium complex to try to get a handle on the electronics of ligands by that rotation rate. Again, if you're interested in learning more about this, talk to me in office hours. Sterics and electronics are the hallmarks of organometallic chemistry. Every organometallic chemist everywhere in one of their papers or presentations says or rationalizes behavior using the phrase, the subtle interplay of steric and electronic factors. I was once at an organometallics Gordon Conference meeting where the former president of the American Chemical Society, Chuck Casey, said this: the complex web of kinetics and thermodynamic factors is further tangled by the subtle interplay of sterics and electronics, and I think that you can use this sentence to explain basically any chemistry you want. This is the end of lesson 4. We have now covered all the major ligand types in organometallic chemistry, although certainly not all, and next week we will go in and talk about reactions and catalysis.